Okay, so in this video we're going to be looking at the sigma notation. Okay. And the symbol we use for sigma is the Greek symbol there. Okay, so sigma. So if I have a sigma, okay, with a number b on the top, and some starting letter k equals a, okay, so a is the starting letter, alright, of a function f of k, then it's a short way to write, short for the sum, and what you do is you start at a, so you put a into your function, evaluate it, plus the number that comes after a plus 1, okay, plus f, a plus 2, plus all the way till you end up at your last number, which is at the top of your sigma, f of b. Okay, so you're just putting in one number at a time in your function, but adding up as you go, you're summing it up. So note, a quick note, that a and b are integers with a less than or equal to b. Okay, so b is always normally the bigger letter. It could technically be the same value as a, but it just means you're not summing up very much. But a is normally the smallest letter. Okay, so all you're doing is whatever a is, that's your starting off number. You add up till you get up to b, and you just keep putting it into your function every time. Okay, and add them up. So we'll look at a few examples. Okay, just to highlight how this works. Oops, lost my page. Okay, so example 1. Okay, we're going to find the sum of when k equals 1 up to 4 of the function 2k plus 5. Okay, so we're going to do that. So that means I'm going to start off by putting k equals 1 into this function, then put k equals 2 into it, k equals 3 into it, k equals 4 into it, one at a time, stop at 4, and add them up as I go. So that would be, if I put k equals 1 into it, first it's going to be 2 times 1 plus 5. Then it's going to be when k equals 2, 2 times 2 plus 5 plus 2 times 3 plus 5 plus 2 times 4 plus 5. And I can stop now because I've went all the way up to 4, which was my b value. Okay, that would give us the number 7 plus 9 plus 11 plus 13, which would give us an answer of 40. Okay, so the sum from k equals 1 up to 4 of that function would give us the answer 40. Okay. Example 2. So this example is going to highlight that not all summations have to start at 1. Okay, so we could start, for example, in this case when k is 6, all the way up to when k is 8, of the function 1 over k bracket k minus 1. Okay, so we're starting off actually here at 6. So if I do that, put in the value k equals 6 in first, that's going to be 1 over 6 times 5. On the bottom, yep, 6 minus 1 is 6 times 5. Plus, then put 7 into it, 1 over 7 times 6. Plus 1 over, put 8 into it, 8 times 7. Okay, that gives you the fractions 1 over 30 plus 1 over 42 plus 1 over 56. And adding them up and simplifying, you would get 3 over 40. Okay, so that would be the sum of that function there. Okay, so there's a couple of examples there. And again, they can get, it doesn't always have to just be sort of short functions. So look at example 3. we're going to start when k equals 2 this time, so again we're not starting at 1, all the way up to when k is 5, and we can have 3k squared plus 4k minus 1. Okay, so again we're starting off here when k equals 2 and going all the way up to when k equals 5. Okay, so putting in k equals 2, so that's going to be 3 times 2 squared plus 4 times 2 minus 1. We'll have to evaluate that. Then it's going to be putting in k equals 3, so it's going to be 3 times 3 squared plus 4 times 3 minus 1. And k equals 4, 3 times 4 squared plus 4 times 4 minus 1. And lastly, when k is 5, 3 times 5 squared plus 4 times 5 minus 1. Okay, so we're just putting in the values one at a time into a function. That would give us 19 in the first term plus 38 in the second bracket, I should say, 63 in the third bracket, and 94 in the last bracket, which then give us a final answer, if I added them up, of 214. Okay, so that's just 3 examples about how to use the sigma notation. Okay, starting off point is put in the function, and you add up every other number that you put into your function, get a total, okay, of the functions there. Okay, stopping at the value of b at the top. Okay, so there's a couple of properties I want to show you in this video as well. So property 1, so these properties will be very handy for us throughout the topic of series and sequences. So property 1 is that the sum, starting off at k equals 1 up to a value n, okay, of a function f of k plus g of k, okay, then that is the exact same as the sum of k equals 1 up to value n of f of k plus the sum as k equals 1 up to n of g of k. Okay, so if you've got 2 functions that are getting added together, then you can split them up and take each sum separately, then add up your final answer. Okay, so that's just what that property is highlighting there. Okay, what we'll do is we'll prove this. So the proof of this, okay, so if I start off with the left hand side, so that's f of k plus g of k, all in the sum is k equals 1 up to n. And what that will look like, that's going to start me off as f of 1 plus g of 1, that'll be my first term, plus f of 2 plus g of 2 in my second term, plus f of 3 plus g of 3, plus all the way up to f of n plus g of n. Okay, so that's what that would look like if I put in the values from k equals 1 all the way up to k equals n. I can split them up, so I can have just all the f functions to start with, so that would be f of 1 plus f of 2 plus f of 3, all the way up to f of n, plus, and do the same for the g function, g of 1 plus g of 2 plus g of 3, all the way up to g of n. And what that really is, that first bit with all the f's in it, that is the sum, starting at k equals 1 up to n of all the f function, f of k, plus the sum is n, so it's k equals 1 up to n of the g function, g of k. Okay, and that's me proved. That's me got the right hand side. Okay, so you can see that that is proving that that property 1 holds. Okay, last property of today. So property 2. Okay. Again, another very useful one for us, and we're going to be using this one a lot, is if A is constant, then if we have the sum as k equals 1 up to n of a constant multiplying a function f of k, then that is the same as the constant multiplying the sum of f of k. Okay, so the constant just comes out the front and multiplies it all. Okay. Again, we'll prove that just to show that this holds. Okay. So again, if I start off with the left hand side, so as k equals 1 up to n of a of f of k, remember a is just a constant, then what that's going to give me, every time I put a value of k equals into it, will be a of f of 1 plus a of f of 2 plus a of f of 3 plus all the way up to a of f of n. Okay, so that's me putting in all the values for k equals 1 up to n in my function. Take a common factor of a out, so that's going to be f of 1 plus f of 2 plus f of 3 plus f of n. Okay, so common factor of a out. So that means that it's going to be a multiplied by the sum of all the functions of f from k equals 1 up to n, which is the sum is k equals 1 up to n of the f function f of k, okay, which is my right hand side. And that's that proven as well. Okay.